All right, hey, good morning, everybody.
Good morning. Good morning. Good morning.
So, looks like most of us at least got the word on the change in modality today. Um, just kind of erring on the side of caution, because the forecast says it's going to keep raining. And I did have a few students already who emailed and said they wouldn't be able to make it to campus. So, we'll do this remotely today. We'll be back to in person on Monday. But this should work fine. So I'll be recording. Sorry, go ahead.
It's snowing at my house.
Yeah, it's still snowing here. It's like the really big, fluffy flakes coming down, and it stopped for like 5 minutes, and then it started again. So we got some weather. So I'm recording the lecture today, and I'll post a link to the recording on Canvas sometime after class. Let me throw a note up here. Or not. Alright, hold on a second. I haven't done this in a while, so. Today is Wednesday. All right, there we go. Yeah, so good morning and welcome to week 8. So short week today for Monday, Wednesday classes, only one meeting. And then next week is week 9. So first thing I want to do is remind people about your service learning project. So the presentation is on the last Tuesday, and again, that's going to be in person, and it'll be in the Collaboratorium from 3 to 5 on March 7th. The SLP final upload, that was originally marked as being due Thursday, and if you turn it in by Thursday, you'll still get credit. But since we're doing this class's presentations in person, I want to have a chance to get your posters printed out. So if you make your upload by Tuesday morning, I will go ahead and send those to the printer, and you will definitely have a hard copy of your poster to use during the presentation that last week. If you turn it in by the original deadline, which was Thursday, I will still try to send it to the printer, but I can't guarantee because a lot of things don't happen on Fridays now on campus. So that's the reason for the earlier deadline. But again, if you still turn it in by that original Thursday deadline, you'll get full credit. I just can't guarantee that I'll get a hard copy to you in time for the presentation. All right, so let's run through PA3 questions. If there's anything anybody wants to go over. So that was the SLP reminder. So yeah, let's talk about PA3 questions.
I have a quick question about the SLP.
Mm-hmm.
What's that extra credit module?
That doesn't exist. So I should be doing the student view. So there's no extra credit.
Oh, for sure.
Yeah. That's something that we've done sometimes in the past for different reasons, but all right, let's see. So someone asked in chat, could you show us one last time how to do the delete function? Does not have to be the last time, but yeah, I can definitely show you or go over deleting from a binary search tree. And so the first thing to remember is delete is recursive. So let's delete from a tree with a given root. Let's find this license plate and delete it. And if the tree is empty, then we have nothing to do. So if the root's null, we can just return null. And if you guarantee that you never call this on a plate that doesn't exist, you should never hit this edge case. But if you've got a random tree and you just say, hey, I want to delete this plate, I don't know if it's actually in the tree or not. If it's not in the tree, eventually you'll get down to where the root is null. So depending on how you insist on calling the delete function, whether you call search first, you may or may not need that edge case check. It doesn't hurt to have it in, though. So if we get past that, and there is stuff in the tree, we can do the following recursive operations. So let me say if plate is less than root arrow plate, meaning that the plate is in the left subtree of the tree. And remember, when we do this comparison, what function do we use to see if something is bigger than, less than, or equal to another string?
String compare.
Excellent. So use string compare. So if it's... Say again?
Do we actually return null in the first line, or is it...
Yeah, so you always want to return the root of the new tree. And if the tree is empty to begin with, the root is null, so just return that root, which is null. So you could return null, or you could return root.
I think I like returning root better.
Okay.
It's more stuff, and you know you're returning root.
Yeah, that's more consistent.
Yeah, null isn't just a flag, it's the actual root.
Right, right. So if the plate sits in the left subtree, then we use our delete function on the left subtree to delete the plate. And since delete always returns the root of the tree, we're going to change the root of the left subtree to whatever delete gives us. And then we're going to return root. On the other hand, if the plate is bigger than the root, delete from the right. And then return the root. Otherwise, we want to delete the root. And this is where it gets exciting. So deleting the root of the tree is the non-recursive case, and that's the one that gets into all the special behaviors. So the first special behavior is if our tree looks like this. Right, if it's got stuff to the right, but there's nothing to the left. So what's our normal algorithm for deleting the root? We replace the root with the largest thing in the left subtree. So we have an edge case if there is no left subtree. So first thing I would check is if root left is null. And this is what we were calling case 3. And in case 3, we simply take the root and move it down to its right child. So root equals root arrow right. We want to, of course, free the old root and then return the new root. So case 3 is pretty short, right? If there's nothing to the left of the root, just move the root down to its right subtree's root and return that as the new root. Save this first so you can free the root. All right, the more general case is where we have stuff to the left. And so here the goal is replace the root with largest node in the left subtree. And the whole challenge here is figuring out what that largest node is and how to do that replacement. And so this breaks into a couple of cases. So one possibility is we've got a setup like this where the biggest node is the immediate left child of the root. And it's only a special case because the algorithm we're going to have to use, the loop we're going to have to do to find the biggest node, doesn't really, it's not needed in this case, right? If the immediate left child has no child on the right, this is the biggest node. So let's do something like this. Let's do b equals root arrow left. And let's set p equal to b. So we're going to call this node both p and both b. And normally, you know, what we're going to do is we're going to march down this chain until we can't get any further to the right. But in the edge case where there's nothing at all to the right of this, we have our case 2. So if b right equals null, then we're in this situation. And here what we're going to do is we're just going to have this adopt the original root right child. Right? Since this is the largest node, it has nothing on the right, it can adopt this entire original right subtree on its right, and that removes the root from the tree. So we're still making this biggest node the root, but the code for doing that is particularly straightforward. So if b right is null, set b right equal to root right, free the root, and then what do we return here? We return b because b is the new root of the tree. And that's important. If you return root, everything goes haywire. So this is the new root, so we return that. And that takes care of case 2. So case 3, we need to find p and b. Alright, so what have we done so far? We started off, here's our general case 3. We started off with p and b being this node right here, the immediate left child of the root. And so we're going to set b to be p's right child. So we're going to say b, this is case 3 still, b equals p arrow right. And my comment here is b is our tentative biggest node, and p is b's parent. So we're going to march through this tree, and we're going to try to find the actual biggest node, which would be this node down here. And when we get there, we want p to be its parent node. So we're doing the march of the temporary variables that we know from our linked list code. And we've seeded this by setting b to be this node and p to be this one. So we're going to want to loop. And we're going to loop until b is this last node. So if b is the last node, we know b right is null, so we can say, well, b right is not null. And we just do the march. So we set b equal to b right, and we set p equal to p right. Alright, so what does this look like? B has something to the right, so we move B down and we move P down. B has something to the right, so we move B down and we move P down. We keep doing this until we get to this situation. And at this point, B has nothing to the right, we exit our loop. So now B is our biggest node, P is the parent. So the last thing we do is have P adopt B's left child. Because B is going to become the root of the tree, which means its left child is going to be right here. And so anything it has to the left is going to get abandoned. So we're going to have P adopt B's left child. And so we can do that because we know P is not going to have anything on the right, because B is going to get moved up to the root. So this is P right equals B left. So that makes this link. And then finally we can say move B to the root. So that means B left equals root left, and B right equals root right. And then free the root, and then again return B, because that's the new root. And again, just to note what's actually happening here is B is picking up all of this stuff on its left, and it's picking up all of this stuff on its right. Right, and we don't want to copy data from here into the root node. We actually want this node to become the root, which means we're going to change its children. And anytime we're working with these data structures, usually we just want to change pointers. In this case, the data itself consists of 3 strings of, arbitrary length. If we were to copy that into the root, we would need to, free the data here and reallocate, and then string copy and so on. We don't want to move the data, we just want to adjust pointers. So we're going to leave this node as the node containing B's data. We're just going to change its left child to point here and its right child to point here. So that's what those will do, and then we free the actual original root. So lots of different cases to deal with. But if you do it in pieces, like I say, start off, forget about the recursion, just write something to delete the root, and just test it on deleting the root, and just put these cases together one at a time. Yeah, you're welcome.
Professor.
Yeah.
When you say free root, do you mean free the plate free first and free last, or root plate root first, root last?
Yeah, so freeing a node like the root would be, free root arrow plate, root arrow first, root arrow last, and then free root. So all 4 pieces.
Thank you.
Yeah, thanks for asking.
So, I'm having an issue where when I try to delete a leaf node, when I print it, when it prints it, it doesn't actually delete it, it just replaces its value with, the plate value with null.
Did you get my response to your email yesterday?
I did, and I fixed that, but it's still doing that.
Interesting. So try, let's see. One thing is, if you can replicate this with a really small tree with only 3 or 4 nodes, get it to that state, and then go into GDB and start from the root node and make a picture of what's pointing to what, and see where that node is coming from. If it's the deleted node that's still appearing, that's one thing. If it's a node that should be in your tree but the root got changed, that's or the plate got changed, that's a different thing.
Well, I'm using a small, I kind of manually made a tree.
Good.
Only a few trees, and the value is being replaced with null. That is one that like that's definitely the one I'm trying to delete.
Okay. So it sounds like the node is somehow still remaining in the tree or still accessible from the tree. And so I think if you start from the root and look at the left and right values and then look at those and dig through it and build a picture, you can figure out which node in your tree is pointing to that deleted node. And once you found that, then it's a question of you know, figuring out what line of code is supposed to break that link but is not breaking that link.
Okay, thank you.
Yeah. And remember, in GDB, you can say things, you know, like print root, arrow right, arrow left, arrow plate with a star. And this will say star to the root, go to the right, go to the left, show me what the plate is. And so with a few of these, you can make yourself a picture of, you know, what's where. And as usual, if you can get to office hours tomorrow, I can help you in there too. All right, other questions?
In the pre and post order printing,
Yeah.
should it be more or less alphabetized?
No, absolutely not. So the in order, which is left node right, that should be absolutely alphabetized by plate. But the pre and post order, completely random. I mean, it can look completely random. It's not, but nothing to do with alphabetical order.
Because they're coming out more or less alphabetized. I don't understand it. It's not perfect like in order, but it's close.
That's interesting.
If your input's alphabetized, it could possibly come like that.
Yeah, if your input's ordered, then there'll be more order. But if you have sort of randomized input, it's a good point.
It's the exact same database as everyone else is using.
It's the test one?
Well, wouldn't it print like certain sections in order, just based on the fact that you're printing the whole left side of the tree and the whole right side of the tree, even if you don't print it in that order, so the whole thing wouldn't be alphabetized, but certain sections would be?
So no, but that tells me or reminds me what it might be going on. So let me tell you something that I usually see happen when people write their code. So people will write the in order first, and so they'll say, you know, node left right. Sorry, they'll do the in order, left node right, and they'll say, you know, left node right, root left, and then they'll print the root, and then they'll do left node right, root right. All right, and then they'll say, okay, well, I want to do pre-order first. So they'll copy and paste, and they'll say, let's do node left right, and they'll move the print statement up here. But if you don't change these to node left right, you get the wrong output. And in particular, that output will be mostly alphabetized. So double check your code and make sure you're not accidentally doing something like this. Does that make sense?
Looks fine.
Okay. All right. Well, let me see what the sample does then. I don't want to put it through more. Yeah, that won't work. Did I call it plate?
Plate 3.
Thank you. I'm gonna go up 1,000 lines. getting there. Here we go. So left, right node, so post order.
More or less alphabetized.
Yeah, so lots of A's, a B, A's, B's, C's. Interesting. So node left, right is going to start at the root and move down. And that should be sort of decreasing order. Left, right node, post order is going to go down deep first, which will be, you know, beginning of the alphabet. And, yeah, so I guess that might make sense.
Yeah, all the A's appear together, but they're not in order necessarily.
Yeah. So, node left, right, I can believe would be roughly alphabetical.
You know those two are on the top because they're at the top.
Right. That's interesting.
Well, that appears to be exactly what I'm getting, so...
Okay. Well, you should be good then. But yeah, that is an interesting observation that that it tends to be largely sorted, including the pre-order, which I'm kind of surprised by. I mean, our first one's not. So yeah, these are slightly reverse alphabetical. In the second, oh yeah, it's interesting. Well, if it matches my output, you're good, but that is curious. And yeah, using diff is a nice way to compare output. If you match the exact output with, you know, punctuation and so on, you can take all of this and throw it into a file. So I can do this and say start dump and then exit, and now I've got my output in a file. And you can do that with your code, do that with the sample code, and then just run the diff command and see how it did. One other note as far as the order of these things, we have 1,000 nodes, and so what would be the ideal tree height for 1,000 nodes if our tree was balanced? Like roughly how deep do you think a node would have to get?
About 10?
Yeah, the height's about 10, so log base 2 of 1,000. 2 to the 10th is 1024. So a height of 10 would be sufficient for all this data. It's telling us the tree height is 21. So, and 21 is big enough for, you know, 2 million nodes. So our tree is very, very sparse. It's about 1/1000th as full as it could be for the height. And that...
1/2000.
Yeah, 1/2000th. And so that may be part of why we're seeing this kind of peculiar ordering. And I think if it was, if the data came in a way that gave you a balanced tree, then I think we'd see the breakup of the ordering more clearly in the other traversals. All right, cool. What else? Yeah, and diff-w is good.
to tar my file, I use the BSD tar, and upon extracting it through Linux on the GNU tar,
Mm-hmm.
it gives me ignoring unknown extended header keyword.
Okay.
It'll extract fine, but I don't know if that'll cost me any points.
That won't cost you points as long as I can extract it and the code compiles when I say make. But if you're in doubt, I would say just tar it up on the server.
Okay, I already submitted it. Would I be able to resubmit?
Yeah, you can resubmit until the deadline. I'll take whichever one is there.
Okay, perfect.
Yeah. Now let's see. Question on the free function. What a good way to go about it be to traverse like we do with printing. Basically, yeah, that's basically what the free function is. So treefree. So if root is null, return. So what's the right traversal order to follow for freeing the tree?
Left, right, null.
Yeah.
Left, null.
Yeah, so we want to do post order, so tree free root left, and then tree free root right, and then free root. And remember, freeing a node is more complex. You have to free the plate, the first, the last, and then the node itself. But yeah, we need to do this last so that these don't segfault.
You could just make up a function called nodeFree that does all of that.
Mm-hmm. Yeah, perfect. So instead of calling free, make a node free, and then call node free, and that can free the plate first, last, and then the node itself. You said any small differences, even punctuation might cost points, right? No. I mean, maybe I said that, but I don't mean that. Let me see what I say. So if you want to use the difference function to check your output against mine, you need to have exactly the same output. Otherwise, difference will say every line is different. But if you've got basically this information in your output and so on, you're good to go. So I mean, if you don't put a colon there, or if you do uppercase name, or say owner's name or something, I'm not worried about that. Don't worry about it. But what I do want you to do is make sure that your output is in this order, right? Show me the tree height, tell me if it's balanced, do the in order, pre-order, post-order. Do it in that order, because that I'll potentially get tripped up on. All right. More questions? Yeah, it's snowing super heavy now. I got trees blocking the back window overhead, so it's not coming down a lot there, but it's coming down really heavy in the front.
I have another question.
Okay.
So, in my code, I was able to fix it so it'll delete a leaf node, but so it'll delete a leaf node that's on the end of a left subtree, but not one on the right.
That's bizarre. It should be no difference unless there's a glitch somewhere in your recursion. So make sure you're doing these comparisons right. Make sure you're going from the right and assigning to the right, or deleting from the left and assigning to the left. And if you got that right, it shouldn't make any difference, because the action part of the code is just deleting the root of a tree, and if it's a leaf node, it's just going to be a case 3.
How did you pipe in the output of dump command to a file?
So I just ran my program and I said greater than file name, and everything that this sends to standard out will go into this file. So you have to work blindly and just, know it's time to type a command, type in your command, and you won't see anything, but it all goes into that output file. And if you prefer, you can pipe it into T, which is like a T pipe, and so the output goes two places. One goes to standard out, the other goes into this file. But depending on buffering, that may or may not be significantly better than just redirecting output, because it's prompting me, but I don't see it because it's buffered. But I can say star dump, and now I see some of my output, but it's not showing me all of it because the output is buffered. But that can help a little bit. And then same thing, my output goes into a file. So that's another option. Yeah, if you don't find something in your code, hop into Office or send me a note. All right, other PA3 questions.
So I was just reviewing what you were going through in the delete function.
Yeah.
And I was wondering I don't know which case you called it, but when there was children on the left of root, did we just automatically assume there was something to the right of that left child?
No, those are that's the difference between case 2 and case 3. So if we have a situation where we've got our root and we've got stuff over here, but this is null, then this is the largest node in the left subtree. This becomes the new root. It's the same prescription as usual, but we do something a little different. We don't have to move down this chain to find the biggest node. The biggest node is right here. And so that I've been calling that case 2 and treating it as a bit of a special case. And the prescription here is just have B take on root's right child as its own right child.
Okay, yeah, I think I just wrote it down and then in my notes wrong.
Okay.
Because I immediately made E root left and E T right, which you can't just automatically assume.
Right, right.
Thank you.
Okay, welcome. All right, anything else?
I'm sorry, can you show the recursion that you wrote down one more time?
Yeah.
Thank you.
Mm-hmm. Here, I'll tag that.
Professor, I have a question about the balanced function.
Yeah.
I was assigning left is balanced and right is balanced as integer variables.
Okay.
I realized though that I wasn't doing anything with those. I kind of ended up just checking the absolute value. And I wasn't sure what I should do with the integer that, left is balanced or right is balanced returns.
Okay.
You could try, instead of the if absolute value or whatever condition, you could try if left is balanced and right is balanced and
Mm-hmm. Yeah. Exactly.
I wasn't sure though what that was actually returning, because I ended up doing that, but I guess I couldn't understand if it made sense or not, if I was actually checking for the right thing.
Yeah, so assuming you've got these 4 variables, so left balance, left height, right? So the balanced function, 1 equals balanced, 0 equals not balanced. And the height is just a height, so it's an integer. And so the tree is balanced if the following happens. If L-bal equals 1 and R-bal equals 1 and absolute L height minus R height is less than or equal to 1, then it's balanced. And so you return a 1, otherwise you return a 0. So if you only check the height, you'll get the right answer sometimes. But we can have certain pathological cases where the heights are similar, but the tree is not balanced, and the way that would look is something like this. Right, so left and right height, left and right subtrees have exactly the same height, but the tree is definitely not balanced because this left subtree is not balanced. So if you don't check those, then in some cases you'll mistakenly think the tree is balanced when it's not.
So for what I was talking about earlier, I added in a test print, and it looks like what my delete is doing is that for a right-hand leaf node, it's reading it as a null root. Do you have any idea what could be causing that?
No.
If this is about trying to discover what case it is, you could just be looping too far to the right, and you're checking is the right. This is the biggest null. You need to be checking it. The biggest arrow right is null. I don't know if that's null or not.
Check for root equals null is at like the very top.
So at the very top of everything, you check to see if the root's null, to know that you've got an empty tree.
And then it's returning the print function that I put inside of that.
So are you saying that your final recursive call to delete is being given a null root?
That's what it looks like. Because,
Interesting.
like, when I run it, I have a print statement in my if root equals null that says like you can't delete from an empty tree.
Okay.
And then when I run it, that prints. So I think it's reading that right-hand leaf node as null.
All right. So here's my suggestion for GDB. First of all, definitely go in and make yourself that picture of the tree using what GDB tells you, right? Not using what you think the tree should be, but start with the root and look at root arrow left, root arrow right, and keep following those links until you've gotten to where all the pointers are null, and make that picture of what the tree looks like. And now put a breakpoint on delete and run your delete command. And every time that you call delete, right, it should tell you what the root is. It'll give you a memory address, and compare that to where you are in your picture and see how it's moving down from the root to the left and the right to find the root node that you want to delete. And it could be, going off the rails somewhere, moving the wrong direction. Or it could be that it's going too deep, making one too many recursive calls somehow. But if you set a breakpoint at the start of delete and actually look at the address of the root that it's taking in as the root of the tree, that should tell you what's going wrong. But you got to make that picture first by hand of what your tree looks like, what the plates are at each point, and write down at least the last few digits of the memory address for each of those nodes. And then GDB will guide you right through it. Usually. Yeah. And remember that if you do this twice, those memory addresses might change. So if you do it a second time, double check the memory map, make sure you've got the same addresses. All right. And did that answer the earlier question about balance, about what to do with these return values?
Yes, thank you.
Okay, cool. All right. Anything else on PA3? All right. Let's go back to talking about dynamic programming. And as I mentioned last time, let's talk about the egg drop problem. And this is a fun exercise to think about. So the setup is you have a basket of eggs, and the eggs are all identical, and your goal is to figure out your background goal is to figure out what the highest floor is that you can drop an egg from without it breaking. Right? That's sort of the background goal here. So and we assume the eggs are identical. We assume if you drop an egg and it doesn't break, it doesn't become damaged. So if I drop it from the 10th floor and it survives, I could drop it from that 10th floor 1,000,000 times and it'll still survive. Right? So these experiments don't change the nature of the eggs. And the question is, given a certain number of eggs and a certain number of floors in the building, what is a guaranteed sufficient number of experiments to run? So this is a little confusing. So our real goal is determine the minimum, the smallest, guaranteed, sufficient number of experiments in order to answer the question. And the question is, what's the highest floor you can drop an egg from without it breaking? So the function we want to write is trying to determine the smallest guaranteed number of experiments that will answer that question. So number of experiments required to answer the question. So what does this mean? Let's say I have 10 floors in the building and I have 4 eggs in my basket. All right, it's possible that I will drop an egg from the first floor and it will crack. And so with one experiment, I've answered my question. But it's also possible that, I'll drop it from the first floor and it will survive. And so I'll drop it from the second floor and it cracks. So now I know that the first floor is the highest floor. It took me 2 experiments. Or, it may be that it will survive from every floor. And if I happen to try dropping it off the 10th floor first and it survived, I've got my answer in one experiment. But we're looking for, what's the guaranteed sufficient number of experiments? The smallest guaranteed sufficient number of experiments. And so we need to look at all the possibilities, right? And all the different ways that I can run my experiments. I might choose to drop it off the 5th floor first, cut my building in half. And if it survives, then I can say, okay, so it survives floor 5. It also survives floors 4, 3, 2, and 1. So now I only have to check floors above 5, and I still have 4 eggs. But if I drop it from the 5th floor and it cracks, now I know that I only have to check floors below the 5th floor, but I've lost an egg. I only have 3 eggs now. So this has the feel of subproblems. And it's harder than predicting high-low. High-low, we can say, you know, if there's n floors, then log n is guaranteed sufficient as the number of guesses you need to answer the question. In that case, the question is, what's the magic number that you're thinking of? But this is a harder version of high-low because some of our experiments may reduce the number of eggs we have. And if you don't have any eggs left in your basket, you can't run any experiments. So if you only have one egg, how do you figure out what the highest floor is that you can drop it from without it breaking? We went over this. Yeah, start off with the first floor. If I start with the second floor and it breaks, I don't know if it would have survived from the first floor, but I have no eggs left to answer that. So if eggs equals 1, we just have to start from the first floor, second floor, third floor, fourth floor, and so on. And in that case, you know, we may get lucky and get our answer after 3 experiments, or we may get unlucky and it may be that we can survive from the 10th floor, and we won't know that till we've run 10 experiments. So if your number of eggs equals 1, number of experiments required is equal to whatever your number of floors is. So we're going to have E eggs, and we're going to have F floors. So if you only have 1 egg, number of experiments is the number of floors. In other words, we can't promise someone that a smaller number of experiments will answer the question. We need potentially to run F experiments. If the number of floors is equal to 1, the number of experiments we need to run is just 1. We just drop an egg from the first floor. So these are base cases for a function we want to define, which I'm going to call, what should I call it? I've got sample code.
Attempts.
Yeah, attempts. So attempts E comma F returns the smallest guaranteed sufficient number of experiments required to answer the question.
Okay,
Alright.
so we're not actually trying to find the floor, we're trying to figure out how many attempts it would take to actually find
Exactly.
the floor. Okay.
All right. So I'm differentiating. The question is, what's the highest floor you can drop from? We're not answering the question. We're saying how many experiments might you need to answer the question.
We're getting a pricing estimate.
Yeah.
For our time, not for the eggs.
Yeah. All right. So we have some base cases, right? If E equals 1, we can just return F. Because with 1 egg, we can't afford to have a bad experiment, so we're going to try floor 1, 2, 3, and so on. If F is equal to 1, we only have to try 1 experiment. Just try dropping from floor 1. Otherwise, we need to do something recursive. And this might take some effort to wrap your head around, but I'm not going to ask you to code this. It's a fun algorithm to think about. So, otherwise, we're going to have to do an experiment. So let's say we drop from floor I. So suppose we decide, okay, I'm going to drop one egg from floor 6. All right, there's two possibilities. The egg breaks or the egg survives. So if the egg breaks, then what happens? What do I find out if dropping from floor 6 causes the egg to break? What do I know?
That the floor it needs to be dropped from is lower.
Yeah, the floor that I'm looking for is somewhere below 6. I can ignore all the floors above. If it breaks from here, it's certainly going to break from a higher floor. That's one of our assumptions I didn't explicitly say. So the number of floors we have to explore is smaller than the original number of floors. And what about the number of eggs we have to run these experiments?
It decreases by 1.
Yeah, we lost an egg, so the number of eggs goes down. So let me call attempts, and let me do egg minus 1 comma floor minus 1. And that's, I minus 1, because we tried floor I. And I'm going to call that A1. So that's the number of temps that we need to determine where our magic, to answer the question once we've dropped an egg from floor 6. So the total number of experiments we need to answer the original question is one experiment where we dropped from floor I, followed by however many experiments it takes to answer this reduced question. Given this many eggs and this many floors, what's the answer to the question? So A1 is just 1 plus this recursive call to attempts. On the other hand, if the egg survives, well, we need to answer a different question. We have the same number of eggs we did before, but in this case, if it survived from floor 6, then our critical floor is somewhere above that floor. So it's somewhere from the top of the building down to one above the experiment we just ran. And so here the number of floors would be the number of floors in the building minus the floor we just dropped off, plus 1 because we already did an experiment. All right, and which of these do we want to consider to be our answer if we drop from floor I? We have to pick the larger of these two, because this is the number of experiments we need if the egg breaks. This is the number we need if the egg survives. Well, if we say, okay, so A1 is sufficient, well, if A2 is bigger and the egg survives, this won't be enough experiments to answer our question. So we need the larger of these two numbers to give us the answer. How many experiments do we need if we start from floor I? So I'm going to say answer equals maximum of A1 and A2. And our goal is to determine which floor we should drop from first to give us our best possible answer. So I'm going to do something like best equals, and I don't know, we'll initialize it to infinity, or maybe floors plus 1. And then this can be a loop for I equals 1 to F. And in here, if our answer is smaller than best, then set best equal to our answer, and that's the end of our loop. And then at the end of all this, we just return best. So this is like the smallest of the largest of our 2 attempts for each floor. So it's a extra bonus weirdness. But that's a recursive solution for the egg drop question. So a few base cases.
Wouldn't it be best to just try halfway through either side?
You can do that for the first one, but again, if you only had 1 egg, you can't start from the middle, because if your egg breaks, you can't answer the question now.
Okay.
So if you have 2 eggs, you could start from the middle, and if it survives, you've got 2 eggs and a sub-problem, but if it breaks, now you've got a smaller problem, but only 1 egg, and that one you have to start from the bottom and go up sequentially.
Okay. It seems like it would be easier to find as a not as a procedural thing, but as a loop. Essentially binary search until you're down to 1 egg, and then just count the number of floors.
So yeah, you could exhaustively do this, but you know, for your first experiment, you have 10 options in this case, and if the egg survives your second experiment, you have 9 options, and if it survives your third experiment, you have 8 options, right? And so in that situation, you've got 10 factorial different experiments you could run. And so that's at least a lower bound on the complexity of an exhaustive search. And
so we're saying what's the minimum number of attempts to find the floor that it breaks at.
Mm-hmm.
And one of the inputs, or not inputs, one of the constants is which floor it'll break at.
Right.
Like, we want to say, hey, how many floors do you need to test if you have 1 egg? And then we'd say, well, you need to test 10. We need to say, how many floors do you test if it's 1 egg? And then if the egg's going to drop at 8, then we say 8.
Mm-hmm. Yeah.
Okay, that makes sense.
Okay, yeah. And then if you have extra eggs, well, it takes you theoretically fewer experiments, but knowing how many fewer it takes is not entirely clear. So this will definitely get us there, right? And the key is really just sort of this recognition of 2 sub-problems, and we don't know which sub-problem applies. We can't know that ahead of time because we don't know the actual nature of the eggs, but whichever sub-problem gives us the largest answer, that's the one we have to consider as, hey, we might need that many experiments. And so this is you know, not only looping through all the possible floors, but inside each loop we've got a bifurcation of possibilities. So this potentially has a lot of recursion to it. And we need some details, right? So our number of eggs isn't allowed to go negative or 0, right? If we have 0 eggs left, we can't run this experiment. So we need to, you know, deal with negative weights in the knapsack problem, same thing. But from a high level, this is an example of some pseudocode. And so I coded this up a while back. And it codes pretty easily. And I'm using dynamic programming, so I'm saving maximum of 520 floors. So I'm saving for a given number of floors and a given number of eggs, how many experiments we need. So that's my dynamic programming cache. And my function is called egg. Takes number of floors, number of eggs, returns an int. And so here's the base case. If our number of eggs is 1, the answer is just the number of floors. If the number of floors is less than or equal to 0, we return 0. If the number of floors is 1, it takes 1 experiment. And so in the beginning, I check to see if I've already cached a result, and if I have, I return it. Otherwise, I'm going to do all of this, and then at the end, before returning, I'll save my answer in the cache. So that's the dynamic programming piece. So here's my best answer, and I can use floors for infinity because I never need more than floors experiments. And so here's this loop that we just wrote out for floor equals 1 to the number of floors. If the egg breaks, well, we took 1 experiment to figure that out, and we need whatever the number of experiments is for 1 fewer floors and 1 fewer eggs. On the other hand, if the egg doesn't break, then we used 1 experiment to discover that. We have the number of floors in the building minus the floor we just dropped from, so we have the top half of the building and the same number of eggs. And then we set this equal to the larger of break and no break. So if break is bigger, we set it to break. And then if this is better than our best solution, we save our best solution. And at the end of the loop, best should be the number of experiments required. So if we have 10 floors and we have 1 egg, it's going to take us 10 experiments. If we have 10 floors and we have 2 eggs, it will only take us 4 experiments. Ten floors and 3 eggs, it will also take us 4 experiments. And in fact, 10 floors and 20 eggs, it's still going to take us 4. So extra eggs don't help us beyond 2 in this case. And I'm printing out some of the recursion here. So we're trying to find 20 eggs, 10 floors, and these are the subproblems that it tries to solve. And each time it comes up with a solution, it prints out what the solution is. And in this case, it's doing a little bit of work, but not too much. But if we had, 100 floors and 5 eggs, it will require 7 experiments. If we have 100 floors and 10 eggs, it'll still take 7. If you have 106 eggs, it takes 7. 105 eggs, that's pretty good. Alright, if you have 4 eggs, then you have to go up to 8 experiments. And if we take out the dynamic programming, 10 floors and 3 eggs. So 10 floors and 3 eggs. And it's got a lot of work that it's doing. So that's what the dynamic programming is saving us from. And 100 floors, 5 eggs, I don't think it'll finish. Alright, so that's another example of a problem that has these 2 characteristics. We talked about optimal sub-solutions. So we're taking the solution to this problem and finding it by solving smaller problems, right? And so that gives us a highly recursive algorithm, and then repeated subproblems where we're continually recalculating the same solutions. For example, 2 eggs, 2 floors, right? We calculate that a whole bunch of times. And so dynamic programming lets us cache the answers to those subproblems and we short circuit the recursion, or we prune the recursion tree, and that speeds up our execution.
So I'm still a bit confused about about what we're trying to answer with this, because if we're trying to find the best solution for a given number of floors and a given number of eggs, it would have to be for any breaking point.
Mm-hmm. Correct.
For breaking. Okay. So why would we have to go through recursively and instead of binary searching until we had one egg left and then just adding one for each floor we need to search?
Because that may not be the best result. So you're saying play high-low till you get down to one egg?
Mm-hmm.
So if you had 1,000 floors and you did that, and you had 5 eggs, so let's try this. 1,000 floors and 5 eggs. So drop it from the middle.
You got the terminal in the way.
I do. Drop it from the middle. That gets you down to floor 500. Drop it from the middle. That gets you to 250. Drop it from the middle. It gets you to 125. Drop it from the middle. That gets you down to 62. You've got 1 egg left. And now you're going to have to do 61 experiments. And so you'd end up with a total of 65 experiments. But we can do better than that. Let me put my dynamic programming back in. So 1,000 floors, 5 eggs. Oh, can't do 1,000 floors. Hey. Thousand floors, 5 eggs. We only need 11 experiments.
Okay, I really don't get how that happened.
Yeah, it's bizarre, right? So
That's without telling us which.
So suppose you started with an experiment on floor 2 instead of floor 1, right? So we could go by 2 starting from the bottom. We could try floor 2, 4, 6, 8, and 10. And that's going to take us 5 experiments, potentially. But if we survive from 4 and we break from 6, we've got our answer, right? We know that the answer is 5. So
The idea is there's those ones in between.
yeah. And so there's different ways. I should modify this to actually show what the solution is, or a solution. So yeah, that's an intriguing question to try to solve. And like I say, I decided not to give you that one for your programming assignment. Because for all of that complexity, the code's actually not that complex. I mean, the actual recursive function is a few lines. It's just getting down these calls correctly, and that's something somebody much smarter than myself figured out. And I don't know how they did that. Alright, so that's another example of recursive programming. So we're going to do the knapsack problem for PA4. And so let's go ahead and take a few minute break and come back, and then let's play with knapsacks. So let's come back at 11:20, and we'll go through PA4. Alright, so I'll see you back here in a few. All right, we're back. So let's talk about PA4, your final programming assignment for the quarter. So this is posted on Canvas. It has a unusual Monday due date, so it's due on March 6th. So a little less than 2 weeks to work on this one. But that's I believe the last week of the quarter, so I didn't want to have it turned in on Friday because I want to be able to grade it and hopefully get feedback to people in class. So let me pull up my version of it. I have so many windows open right now. All right, so PA4. So PA4 is a exercise in dynamic programming. We're going to use the 0-1 knapsack problem. First thing I want to note is that this is a group project if you want to work in a group. You can have groups of up to 3 people. And I put a bunch of information at the end of the prompt on submission details for how to turn this in if you're doing it as a group project. And we'll talk about those when we get there, but you want to make sure you understand the submission guidelines so that you don't lose points needlessly. So basic setup, you're going to write a program, call it knapsack, and it takes 2 arguments. It takes the capacity of your knapsack, and it takes an inventory or item file showing a list of items, what they weigh, and what they're worth. And your goal is to figure out how many of each item you should put in your bag in order to get the maximum value out of the bag. And so there's sample code as usual on the server. So there's a knapsack.data file, and this is just a sample file. You can copy this and change it, or you can make your own. But the file looks like a description of the object, which is just a string with no spaces, the value of the item, and the weight of the item. So it's a name, value, weight, triple. And then the knapsack program itself, the sample program is just called knapsack. So we're going to say knapsack. If I don't put in the right arguments, it should give me a usage message. Say, hey, put in a capacity and a number of an item file. So if we say we have 20 pounds capacity and we're going to use this data file, it will calculate, hey, the highest possible value is 800, and you get that by putting in 4 of the phones. Phones weigh 5 pounds each. If I run this with a capacity of 19, it gets a different solution. Put in 3 phones and 2 pens. My pens, my phones weigh 5 each, so that's 15. And then put in 2 pens, 2 pounds each, that's 19. So there's my optimal solution there. All right, so the same problem we went over last week. The knapsack problem. So it's the 0-1 problem because you can only answer with a whole number of each item. You're not allowed to put in half a cell phone, for example. And so the way we solve this is with the recursive definition of the maximum value function. And we'll go over that again in a little bit. So program behavior. First thing you should do is open up that inventory file, read the contents into memory, save it, close the file. So you make that memory storage of your inventory, and you can do that with parallel arrays, you can do it with structures, it's totally up to you. But what you want is the ability to figure out the weight and the value of each item in your inventory. And you're going to use that in this MaxVal function. So call a function, for example, MaxVal of x that takes in a capacity x and gives you back the maximum value. And a reminder of what we did in class, right? How does MaxVal work? If your capacity is 0, it returns 0. Otherwise, calculate the following things. The value of item 0 plus MaxVal of the original capacity minus the weight of item 0. And then calculate the value of item 1 plus the maximum value of your original capacity minus the weight of item 1. Calculate each of these and find the largest of those. That gives you the maximum value you can get out of a bag with capacity X. Alright, and so you return that, and that gets used in the recursive calls. Additional details. So we need to keep track of not only what the maximum value is, but what items give us that maximum value. So this is going to make the function trickier, and this is something that you can do at the end of your first pass through this assignment. Your first pass can be just find the maximum value. If I say, here's my inventory item, my capacity is 19, just figure out 642 is the maximum value. And once you've got that completely working, you've figured out the dynamic programming part, you've got all of your test cases done, and you're satisfied with all of that, now go back and redo the problem, but taking into account that you want to know actually which items get you that maximum value. You're working in groups, right, if you like, of up to 3 people. So the time to get this done should be less than if you're doing this by yourself. And if you try to do this while you're trying to understand the recursive substructures, the dynamic programming, the details of parsing the input file, and so on, it's going to be a nightmare, right? So I'm strongly going to suggest leave this for last. Just try to find the maximum value, and then go back and add in the tracking of the items that get you that value. Alright, so you want to use dynamic programming. If you don't, and you try this for a capacity of 1,000, your code will not finish. So you'll want to get that in there pretty quickly, but it's a pretty easy thing to cache. We can just cache keyed off of the capacity of the bag. And so recommended output, right? Show me the inventory file, and then tell me what the capacity is, tell me what the best value is you can get, and tell me the list of items that get you that value. Doesn't have to be exactly like this, but I definitely want all of this information in your answer. All right, reasonable error checking, right? If I run knapsack and I don't give it the right number of arguments, it should throw an error message. If I don't give it an integer here, it should throw an error message. If I have a badly formed knapsack.data file, it should throw an error message. So my knapsack.data file should be a string, an integer, and an integer. And it should be a series of lines that look like that. So if I give it a random file, the parse should fail pretty quickly. And you should print out an error in the data file and just exit. Alright, you also get some simplifying assumptions, and take advantage of these. They will make life a lot easier. We do not need to worry about dynamic memory for this assignment. We don't need to do mallocs, we don't need to do frees. So you can make the following assumptions. The largest inventory file you'll have is 128 items, which means we can make statically allocated arrays of 128 elements to store the name, the weight, and the value of each item. Maximum bag capacity is 1024, which means our cache for storing our saved values can be allocated statically, and 1024 or 1025 entries will suffice for that. The name of the item is going to be 32 characters or fewer and contains no spaces, which means we can use our favorite scanf with a %s format to pick up this first field. So when you ingest from your data file, you can scan it with a %s, %d, %d. and then make sure that that scanf call returns 3. That tells you got a string and a pair of integers. Alright, and then submission, upload pa4.tar to Canvas by the due date. Special details if you're doing this in a group. So, only one group member should submit the code, and you want to coordinate this with the people in the group. Decide ahead of time who's going to turn in the tar file. Additionally, every .c file in your archive should have a comment block in the very beginning with the full name of everybody in the group. And whichever file I happen to look at, if I don't see a comment block in the beginning with names of group members, then only the person who submitted will get credit for that submission. So you want to make sure that this comment block with the names of the people is in that header file. If you've got initials and there's ambiguity with those initials, you can't get credit for it. Right? So put in the full names of each person in the group. Most people, this will be a single .c file, so just put your group member names in the beginning of that as soon as you start coding, right? And then you don't have to worry about it again. If 2 people from the group upload a tar file for this, I'll grade whichever one I come across first. And if that's the one that has bugs and wasn't supposed to be submitted, I'm sorry, but that's the grade that everybody in the group will get. So make sure you coordinate this, right? If for some reason you feel like 2 people need to submit, just make sure that you both submit the correct version of the code. Right? So coordinate with your group members. All right. And then possible deductions. If there's no upload, you get 0 points. Compile errors, you're going to lose half credit because then I have to fix those to grade. Make sure there's no warnings. Make sure there are no seg faults when you run. Make sure you get a solution. And if your solution is not optimal, you lose 30 points. On the other hand, you know, if you want to gamify this, you can get a 70 by efficiently reporting any solution, even if it's not an optimal one. But don't do that, because you miss out all the fun of having coded knapsack. Doesn't run in a short amount of time. This means your dynamic programming is not working, right? That costs you 30 points. And if you've got everything working, dynamic programming is wired in, you get the optimal solution, but you don't show me the correct item counts, that's 15 points. So just like delete in PA3, right? You can do this as your last piece, and it's only worth 15 points. So, you know, a letter grade or 2, but not the difference between, you know, passing or failing. So, and we'll work through the details of the algorithm again today, and look at how we go about figuring out what the actual inventory is. All right, so questions on PA4 logistics or details like that. All right. So let's dig into this maximum value function.
There is a question in chat.
Let's see. Would it make sense to cache results in an AVL tree if you're going to do a lot of recursion? You could, but you really don't have to, because we've got an upper bound on how large a capacity we'll deal with, which is 1024. So a fixed array of 1025 elements will work fine for a cache, instead of searching an AVL tree. So we can just make a cache of 1025, and cache bracket I stores the capacity we calculate, the value we calculated for a capacity of I. So I just got an alert from Clark, and they are trying to decide what to do about the snow for tomorrow. So they've sent a note saying that they met this morning and decided to let things open as usual. But WSU has just suspended operations starting at noon today until 10 a.m. Thursday. So WSU is suspending, and Clark may do the same, but presumably they'll send an announcement. And Tournament of Antiderivatives, which I posted about last week, has been postponed, so until March 1st. All right, so let's look at this business of finding the maximum value for a knapsack. So MaxVal takes an integer capacity. It should return an int. And I'm assuming we've already read in our inventory of items, and we have some arrays, which I'll call weight bracket I and value bracket I. And so if we start with item I, the best value we can get is the value of item I plus the maximum value of a bag that holds our original capacity minus the weight of item I. And so we can say if the weight of item I is less than or equal to the capacity of our bag. In other words, if we are able to put item I into our bag, then we can get this much value from that item plus this much value from the remaining capacity in the bag. And so we can start off with, a best value equals 0. And we can say if value is bigger than best, set best equal to value. And we just loop. So loop over all of the items in your inventory. So typically 0 to n minus 1. And then at the end of all of this, return best. So that's the bare knapsack algorithm just for finding the maximum value itself. And this was the one we went over last week. So initialize your best answer to 0, and then for each item in your inventory, if it fits in your bag, calculate the value you can get by putting that into your bag. And if that's better than your best answer, save it, and then return the best answer. So questions about this before we go on and talk about the actual list of items that get us that value? Let's see in chat. So that was a general question about caching results in an AVL tree. Yeah, you could do that if you potentially had a lot of results and they weren't going to be sequential, right? So yeah, an AVL tree would be a good choice. A hash might also be a good choice if you were storing something that wasn't numeric, right? That could work too. But yeah, that would you definitely want to when you're doing dynamic programming and you're looking up to see if you have a solution cached, you need that to be efficient. And so if it's potentially a large number, yeah, AVL tree could be a good solution. This is a problem CPUs have inside their memory subsystems also. How do you look something up to see if it's in your cache? And that's actually a bit of a hash function. All right, so let's talk about tracking the optimal inventory. And my suggestion here is going to be have something like this. So we've got weight I, we've got value bracket I. But let's also have something that I'm going to call an item count. And item count is going to be an array that says how many of each item do I currently have in whatever situation I'm considering. So we need to change our MaxVal function because we want to get back two pieces of information from this function. We want to get back the actual maximum value, which is an integer, but we also want to get back this item count, an array that says how many of each item from our inventory do we need in order to get this maximum value. And to pass back two pieces of information from a function, you've got a few options. One option is to, pass an argument by reference and have the function modify that argument. The other option is to return a structure. So you can define a structure that includes an integer, which is the maximum value, and also includes an array, which is your item count. And how you want to wire this in C is up to you. But I'm just going to do pseudocode. And so I'm just going to imagine that my MaxVal returns an integer and an item count. And so if my inventory looks like this, and my item count, the first element would tell me how many pencils I have, the second would tell me how many pens, the third is how many books, the fourth is how many phones. So it's just a count. And I can initialize item count to all zeros, which says, hey, in an empty bag I have 0 pencils, 0 pens, and so on. So let me write some pseudocode here. So this is going to be MaxVal of capacity. And this will return an integer, which is the maximum value, and an item count, which is an array showing the number of each item in the best solution. All right, so my initial best solution is 0, and my I'm going to initialize best item count to be all zeros. And we're going to do exactly the same loop here. We're going to loop through each item. If the item fits, we're going to figure out what the value is we get by putting that item in our bag plus filling the rest of the bag. And if that value is better than our best answer, we'll remember that. We're going to do exactly the same thing here. We're just also going to keep track of how many of each item we have in this best solution. So I'm going to have this best item count that goes along with my best integer value. And so we'll loop for I equals 0 to last item. And we'll say if item I fits in the bag, so here I'm going to say try each item, and this is if the item fits in our bag. Alright, so this is pseudocode. I can do whatever I want in here, right? So I'm gonna do something Pythonish here. I'm going to say this answer and this item count come from MaxVal capacity minus weight of item I. Okay, so what are we doing here? And like I say, you have to figure out how you want to do this. Are you going to return structures? Or are you going to pass these as arguments or whatever? But the goal here is I'm going to call this MaxVal function. Remember, MaxVal returns two things. An integer answer, which is the max capacity, and an array showing how many of each item gets me that answer. Yeah, you can return multiple things in Python. Yay. So this says, okay, if I put item I in my bag, my remaining capacity is this. Let's see what the best answer is I can get from that diminished capacity. And this is the amount of value I can get. This is the list of items that give me that value. Alright, so now I have to adjust these because I also have item I in my bag. So adjust these because we also have item I. So this answer equals this answer plus the value of item I. So that adjusts our number for how much value we can get. And then how can we adjust this item count to take into account the fact that we added item I to our bag? Any ideas?
Could we make a global variable and increment?
What would we increment?
The item count?
Yeah. So we've got item count, which says, you know, to get this maximum value, we need this many of each item. Well, inside this loop, what we're doing is we're saying, okay, if I start with item I, this is how much value I can get. And the inventory of items that gets me that is this item count. Except this is the item count we got for this diminished capacity bag. But this solution is based on starting off with one of item I in your bag. So if we take item I and we just increment that, now we've noted that we have one extra of item I, and this is the value that we get. So we've done this, but we've not only calculated the best value we can get, but we've also noted that whatever inventory gets us this MaxVal, we're going to add one more of item I. And now we can do what we did before. If this answer is bigger than best, set best equal to this answer, and set best item count equal to this item count. This is pseudocode. Don't try to do this in C. A lot of this doesn't work in C. You got to make it work. But that's the goal, right? If this answer that we got by starting with item I is better than the best one we've seen, let's remember that best answer, and let's remember the item count that gave us that best answer. And then when we're done with our whole loop, we're going to return our best answer along with our best item count, which also doesn't work in C. But that's how we wire in the inventory to our solution. But one more time, and then I'll stop saying it, right? Forget about the inventory until later. Just start off with this. And then once you've got that working and everything is all figured out, now start tackling the question of how are we going to record the inventory. Because you have to change what MaxVal returns and all this sort of stuff. All right, other questions? All right. So that's PA4. And, you know, I recommend starting it as soon as you're done with PA3. Or if you need a break from the delete function. And my usual comments about, you know, working on subproblems and so on are not quite as applicable here, because really the bulk of PA4 is one function, right? It's just the MaxVal function. If you can write that, you've got, you know, the new part of the assignment done, right? The rest of it is boilerplate stuff from 224, from your first assignments in 222. Processing command line arguments, opening the inventory file, reading it in, storing it in an array, or a set of arrays, setting up structures if you want to make things easier. All of that stuff is you know, stuff you've been doing for some time now, and so I don't expect that to be a source of great challenge or excitement. It's really just this MaxVal function, and it's a single function, and it may only be, you know, 10 lines of code or so. So there's not a whole lot of modularization here. There's not a whole lot of, you know, get this piece working and then add this piece and then add this piece, other than, you know, this one piece of getting the inventory count for each item. So this is one you just kind of jump into, and the dynamic programming, you can add that on at the end, but that's literally just 2 lines of code, one in the beginning of the MaxVal and one at the end of the MaxVal function. And if you code this without dynamic programming, it'll work for small problems, but for larger problems it'll just start to slow down. All right. And group project wise, you don't have to tell me if you're working in groups. You don't have to ask permission. Just make sure it's no more than 3 people in a group, and put everybody's name in the top of each C file. All right. Well, we're going to go on to something else then. If there's no other questions on that. And that's the end of dynamic programming as we're going to cover it here. So let's go back to thinking about trees. And instead of binary trees, let's think about a 3-way tree. So a tree where we have potentially 3 children on each node. And let me ask you a question. Under ideal circumstances, is there some advantage to storing data in a 3-way tree versus a 2-way tree in terms of processing time?
Well, it'd be even faster, right? Because the more it have less layers, which means less distance to traverse to find your information.
Yeah, exactly. Right? If we have...
Slower, I think.
Say again?
The problem would grow slower, I think. It
Yeah.
wouldn't necessarily be faster for small problems.
So the problem grows slower, exactly. It's a different order of complexity. Because with a binary tree, if we have n pieces of data, we have roughly log base 2 of n levels to our tree. In other words, the height of the tree is on the order of log base 2 of n. But with a 3-way tree, this is potentially log base 3. And that is a big difference. It's a difference that gets better over larger n. Now, we spend more memory, right? Because now each node needs 3 pointers, 1 to each of the 3 children. So this is going to require more memory for the same amount of data. But the amount of times we'll need to recurse or loop to get from the root down to a leaf node will generally be smaller. And for very big n, this is a significant difference.
So, quick question.
Mm-hmm.
So instead of like making a tree, right, where it's like you have a pointer to each node, what if you did something similar to like a hash table? And then wouldn't that mean you'd have 1 pointer to the table, and then something that would find the index, and then from there you just have 1 pointer, so it wouldn't take too much extra memory? Or actually it would take less. Right?
So each node was like a hash table?
Yeah, in a sense. So you'd only have 1 pointer to the first spot of the array.
So you're potentially a few minutes ahead of the lecture. Because where we're going is something that kind of does something like that. It's not a full-on hash, but it's a bit of a hash function. So we may address that in a few minutes. And if we don't, we can come back and you can re-ask.
Alright, thanks.
Yeah. So, you know, if we have a tree of height 20 and it's a binary tree, it's got this many nodes in it, so about 1 million. If it's a 3-way tree of height 20, it's got this many nodes, right? And that gets better for larger numbers. So there's a speed advantage to this. So how could we build something like a 3-way search tree, a trinary search tree? Let's think about our license plates. And we have a root node, and it's got some plate stored in it. And we break off in PA3 into one of two directions based on whether the plate that we're looking for or adding to our tree is less than or bigger than this. One way of thinking about that is this plate splits the alphabet in half. If this plate starts with the letter M, then we're saying everything over here is, say, A through L, and everything over here is N through Z. I know we could still have an M in here, but I'm doing a simplified version of this, right? So this root node basically splits the alphabet. And depending on what the letter is of the plate we're storing, we're going to go into the left or the right subtree. So imagine instead if we had 3 children, we could do something like this will be A through H, and this will be I through R, and this will be S through Z. And comparing to M doesn't really make sense anymore, right? But we can kind of mimic what we do with a binary tree by just thinking of, okay, we're going to choose which of our 3 branches we follow just based on, you know, what the first letter of our license plate is. And so if we want to store a license plate like, you know, D, E, X, right, we look at this first letter and say, okay, let's come down here. And this would have 3 children to choose from. And now we need to know which of these 3 branches should we go down to look for this license plate, assuming it wasn't at this node. And we could try to compare it to the node here and use this, but this doesn't really split the alphabet into 3 pieces, right? This splits the alphabet into 2 pieces. But for a 3-way tree, it's not clear that we can do a comparison. But here's what we can do. We can have 3 children, A through H, I through R, and S through Z. But we'll decide which of these to follow based on the second letter of our plate. So the first letter will say, hey, let's come down here. The second letter is an E, that would say, hey, let's come down here. And here we've got 3 children, and this one is S through Z. That third letter will say, let's go down here. So we're taking the idea of a binary search tree and we're sort of twisting it and changing it a little bit. And this is moving into something that's kind of like a tree, but it's actually called a trie. And the idea of a trie is we have these multi-way nodes where each node has multiple children, and we choose which child to explore based on successive letters of the thing that we're looking for. And instead of having ranges of these, we sort of go to the most extreme possibility. And we have 26 children for each node. And we choose which node to go down based on, in this case, what the first letter of our license plate or whatever data we're looking for. Based on the first letter, we choose one of these 26 children.
That was pretty much the first hash function we ever talked about.
Yeah, yeah. So that would get us to one of 26 nodes. But, you know, with hash functions, there's collisions. There may be 2 things stored in our trie that have the same first letter. But if we have, you know, a cat and a cab, well, both of those, there'd be a pointer coming off of here that points to another node. And in this case, the A and the A say, hey, let's follow this A node to a third node. But the cat is going to be stored off of this node, and the cab is going to be stored off of that node. So if we're searching for a cat, we would start off with C, come to this node, follow the A, come to this node, follow the T, and if that takes us to a non-null node, that's where our cat would be stored. And a cab would come down here. Alright, so we'll get into details in a moment. But from a high level, right, this is like a 26-way tree. And in general, how deep are we going to have to go down this tree to find any given word?
The number of letters in the word?
The number of letters in the word. Right? So if we imagine that, most words have 10 letters or fewer, 10 operations to dig a word out of this structure. And so this is order length of word. And if we decide that, all words are 20 characters or fewer, this is an order 20 operation. Well, order 20 is the same as order 1, right? It's a fixed amount of time. And that's pretty sweet. So what's the downside to this structure? Yeah, the amounts of memory. 26 pointers for each node. Well, that's pretty heavy load. But this is a recurring theme in computer science. We can trade off space and time for each other sometimes. And for a lot of our algorithms, we can make a table. By space, I mean memory. And, ideally we would like an algorithm that takes almost no time and requires almost no memory. But we don't find many of those. What we do find is algorithms that take a really long time, but not a lot of memory. But sometimes we can trade off some of that time for something that takes more memory. In the case of a trie, we can cut that time way down, but require a lot more memory. I mean, we do this when we go from an array to a linked list, right? Because the linked list takes more memory because we have pointers, but it's a little faster. When we go to a binary tree, each piece of data has, 2 pointers associated with it. That takes more memory, but our time increases significantly. And so a lot of algorithms, we find that we can move around this space-time field and sort of, pick and choose based on what our criteria are. The really bad problems are the ones that are up here, though. Take a lot of time and a lot of memory. All right, so here's what a trie might look like. Right, so each of these is a node, and I'm going to mark this as the root node, and there's always one root for the entire trie. Think of it as a tree, right? And here's how we use this. So let's put some information into our structure. So let's store the word cat. All right. So cat begins with a C. That gives us our first pointer here, and I'm assuming all of these pointers are null unless we've drawn a line from them. So let's assume all of these are null. and we'll worry about this EOS in a minute. So all of these are null, so we're going to have something to store cat. Well, C is not pointing to anything yet, so we're going to make a new node and have C point to that. The second letter of cat is A. Well, A is not pointing anywhere, so let's have that point to another node, and that's going to store the A. And now in this third node, the T is not pointing anywhere, so we're going to have that point to another node. And in this node, we're going to put a 1 in this end of string field. So these are all going to be 0 to begin with. And when EOS is set to 1, it means the word that got you here is part of our try. So starting from the root, we followed C-A-T, and we got to a node with a 1. That means C-A-T is in our try. Everybody got that? All right. So C-A-B, well, we want to store a C. We see the C is already pointing somewhere, so we don't create a new node. We just follow that over here. The second letter is an A. Well, that's already pointing somewhere, so we follow that. The third letter is a B. B is pointing to null. So we create a new node, and we have B point to that new node. And that's the end of our word, so we set our end of string marker here to be a 1. So now there's a cab in our tree. All right, let's store cats. So start at the root. There's a C. It points down here. Second letter is an A. That points to this node. Third letter is a T. That points to this node. Fourth letter is an S. S is currently null. So we're going to add a pointer here to another node. And that's the S for cats. That's the end of our string. So we'll change the end of string field here. And now we've got cats in our try. Does everybody see how this is working? Cool.
Yeah.
So if I search for the word CAD, well, I'll start with a C. It's not null, so I'll follow the link down here. I'll search for an A. That's not null. I'll follow the link down here. I'll search for a D. D is pointing to null. Nope, CAD's not in our try. So we've got 3 words stored, and we're currently using 1, 2, 3, 4, 5, 6 of these super wide nodes. And so the amount of memory we're going to use grows pretty quickly. But the efficiency of searching for something in here is very high. So if you've got something that, you know, breaks out nicely into, say, you know, uppercase letters, and you really, really care about very efficient access, this can be a good data structure to use. But it's a kind of weird structure. Let me ask you this. The word cat, C-A-T, is that stored anywhere in my memory? Is there anywhere in my memory that I would actually find the ASCII code for a C, followed by an A, followed by a T, followed by a null terminator?
No.
Yeah, it's not actually stored anywhere.
Well, it's probably somewhere, but not anywhere that we know about.
Well, it's not stored anywhere on account of this, right? Could be stored somewhere randomly. But the only sense in which cat is part of the structure is it's coded in the process I follow to get to a particular field where end of string is set to 1. And it's only in the coding it's only in the process I follow to get there that I have this information stored. So it's a sort of quirky version of a data structure in that sense. but very straightforward to implement, right? I mean, you would make an array of pointers instead of having a pointer called, you know, A, B, C, D, E. You could make an array of 26 pointers and, you know, figure out what letter of the alphabet this is, use that as an index into your array. If the pointer is null, malloc a new node, set the pointer to point to that, move down to the next letter. This works great recursively, right? And traversing this structure is interesting if you want to print out every word that's stored. Well, it's not too hard to do in theory, right? Each node here that's not null, if I find a C and it's not null, hey, all I got to do is call my recursive print function on this node with a tag that says, hey, every word that you find in this try, put a C in front of it. So implementing that is a little funky, but you know, the effect is traverse the try with this root and print a C in front of every word that you find. And then if I have yo stored in my tree, you know, I'd have a y pointing to another node, and I'd have o pointing to another node, and down here I'd store the end of string. So eventually I find another node that's not null, and I say, hey, print out every word you find in this try with a y in front of it. And those are recursive calls, so when I'm printing every node here with a C in front of it, I'm going to print out an A. I'm going to say print out every node here with a CA in front of it. And that'll print out a cab and a cat. So these are fun structures to play with. Deletion is a different matter. Deleting from here, if you don't care about the memory, is easy. Just change your end of string from 1 to a 0. But if you want to reclaim memory you don't need anymore, that's a whole another nightmare. But anyway, so that's a try. It's a real thing. We use it sometimes. Memory expensive, time efficient. All right. That's all we got time for today. So Monday we will talk about sorting, and we'll spend probably 2 classes talking about different sort algorithms. And we'll look at, you know, we'll start with a bubble sort, and we'll go through a variety of sorts with increasing complexity and efficiency. We'll compare these to each other. We'll look in some cases at, you know, best case and worst case. And we'll see a lot of interesting things there. So that will probably be most of next week. We'll be doing sorts, and then we're at our last week of classes. So we'll pick up a few more things on that last Monday, yeah, we have one extra Monday for this course, don't we? We have a Monday during exam week, so we'll use that one for review. Well, I'll use the last Wednesday for review, and then we'll pick up something on that final Monday. Does our SLP need to be 100% finished by end of spring term? No. If it's finished and it works, that's great, but that's not a requirement. You want to make progress and you want to document it. Particularly for winter term, a lot of the progress may be backwards. It may be, you know, rescaling the problem. Hopefully by the end of winter term, you've got a pretty good handle on the project and a pretty good sense that it's you know, something you can move forward with. But how far do you get with that? Well, that's a little hard to predict. So no, it does not have to be a finished product. It could be something that, you know, you get to the end of spring and it fabulously blows up. Not literally, but, you know, and you find out, oh, this doesn't work at all. That's okay, right? Learning experience. So, and constant effort, that's all we need. All right. Well, have a good one. If you're in 215, I'll see you at 1 o'clock. I should be on time today because I'm already home. Otherwise, I'll see you next time. All right. Thanks.
All right, I'll see you.
All right. Bye.